It's a pleasure today to have Professor Zheng from the Traveling Institute for Theoretical Sciences at the University of Chinese Academy of Sciences give a talk. He will tell us about continuous non-invertible symmetries. Please join me welcome Professor Zheng.
Thanks, Zheng, for the kind invitation. And it's a great to be back here. So let's. So today I'm going to tell you about our recent work on continuous non-invertible symmetry. And this work is based on, this talk is based on this recent work in collaboration with two fantastic collaborators, Diego de Mastro and Adal Shari. So this is the outline of the talk. So first, I'm going to give you some brief motivation for why this is interesting. And then I'll give you a simple example of continuous non-invertible symmetry, which people have already known for many years, but the level of understanding becomes more and more accurate. And then I'll give you generalized Noether theorem, which it turns out to be very important in finding new examples of this continuous non-invertible symmetry beyond the type of example that I introduced in the second part. And then I'll give you more examples, and hopefully I'll finally explain one application of the non-invertible continuous symmetry. So this is the outline. Okay, so let me start with the motivation. So the central idea of this continuous the generalized symmetry business is the slogan that the generalized symmetry should be thought of as topological operators. Because in the quantum field theory, and because I'm not going to, so because this talk will assume relativity, so I'm not going to distinguish operator versus topological. Okay. And this idea has been very successful in maybe the recent 10 years, especially for discrete symmetries. And you know that, that there are various generalizations, for example, the higher form symmetry, and for the non-invertible ones. And they are useful. There are many uses of these new symmetries. For example, they can guide us to define or find a new lattice model. For instance, you know that in maybe last month or a couple of months ago, there are a couple of papers by Janet and her collaborators who found many lattice models which flow to the critical points between the two different gap faces. So, and the generalized symmetry is a very important guiding principle to help us to design these lattice models. And it can also help us to understand new understanding of the phases and the phase transitions. Yeah, this is basically the Landau paradigm. So usually we say that the Landau paradigm is a statement that the different phases can be organized or can be classified by the pattern of the symmetry breaking. But now, because the notion of the symmetry gets generalized, so previously what's called the beyond the Landau paradigm phases can now be included in the Landau paradigm, including the generalized Landau paradigm. And also it provides new RG constraints. So the symmetries are very important. And one of the main reasons that it's like people discuss these discrete symmetries quite a lot is that there's an underlying mathematical framework for the discrete symmetries. And so the underlying mathematical framework is quite sort of well established, especially in low dimensions. It's called higher diffusion type. Okay. Now, discrete symmetries are very successful. So we need to ask, like, what about the continuous symmetries? Well, if we recall, like, how do we learn about the symmetries? Actually, the first symmetry we learned is the continuous one. Either the space, like rotation, or the charge conservation. So all of them are continuous symmetry. And then later, we learned these discrete symmetries, which we sort of have some more subtle ones. But now, for the generalized symmetry community, the understanding is like in the opposite order. So now it's time for us to go back to revisit how do we generalize. Okay, so if you follow the logic like this, follow this slogan, then for the continuous symmetry, we just put continuous on both sides, right? Maybe let's show you in a different color. And on the other hand, when we first learned these continuous symmetries, we're all taught that continuous symmetry are associated with the Noether current. So, so we know that continuous, at least the ordinary continuous symmetries, are associated with the Noether current. Well, let's call it conserved current. This is the Noether theorem. And for the purpose of this talk, let me emphasize that on the right-hand side, the Noether current is local. Usually we don't emphasize this perspective, but in terms of being important, if we want to generalize. So this is for the ordinary symmetries. This is the ordinary or invertible. But then, how do we generalize to the continuous symmetries, but not characterized by the groups? And we need to ask, like, whether there is also a kind of a Noether theorem for that. And one of the goals of this talk is to explain the generalized Noether theorem. Which means that the general continuous non-invertible symmetry associated with still conserve the currents. But they are non-local. I'll be more precise on what do I mean by non-local, and later. Yeah. Okay. And yeah, so this is one of the goals that of this talk that I try to explain and test this proposal and found many examples of non-invertible symmetries using the non-local conserved currents. Okay. And I have to mention that this correspondence has already been known for a couple of years, but it's just that the people haven't systematically discussed this explicitly in the papers, or and as far as we know, that most of the discussions focus on the direction in this direction, but the backward direction is less explored. So we try to make both directions as transparent as we can, and that's our what is our work is about. Okay, and I have to mention that in particular, this correspondence has already been alluded to by these works, and the work by Yifan Wang and Ryan Songren in 21. Maybe I have to reference the author. And also, very importantly, by so Zheng gave a talk in Simon Center, also in 21, and he mentioned briefly his ongoing work with Yifan and Zheng, naturally, but somehow that ongoing work never appeared. Okay, so this is the outline. So this is the basic motivation of the talk. So are there any questions about that? Yeah. Yeah. Yes. Yes. Yeah. Well, you can, but then you have to work out all the fusion rules. I mean, well, first of all, yeah, fusion rule, F symbols, maybe even R symbols. So all of these higher categorical data are yet to be discovered. And actually, one of the Yinan's recent paper, like the 5-guy paper. So one of the purpose of their paper is to explore the categorical data, but for the ordinary symmetry. Yeah, for all like invertible continuous symmetry. Yeah. I mean, those data have to be at least clarified or explicitly worked out. For discrete, for example, one of the key property of this discrete symmetry is that you can solve the pentagon identity, for example, for the F symbols, and a very non-trivial result is that the number of solutions is finite up to gauge transformations. But for the continuous ones, maybe it's less clear that the number of solutions is finite. Yeah, so that's the motivation. So are there further questions? Okay. Okay, so now let me move on to the second part. So I'll give you a simple example of this generalized or continuous non-invertible symmetry. Yeah, and this example is called the cosine symmetry. A simple example. Okay, And so our discussion follows that by Jacobs from 24th, and also paper by Zheng and Caroline Zhang, also from 24th, and also by Wei Guangcao, Yuan Miao, and Masahito Yamazaki. So these are the main references. Let me start from here. So let's consider a one plus. Well, the example actually works for arbitrary dimensions, but for simplicity, let's work on 1 plus 1b. And so consider arbitrary QFT with U1 symmetry, and also the charge configuration system. And the U1 symmetry, for U1 symmetry, you have a topological operator, which we call the U alpha, where alpha is a 2-pi periodic parameter. So it can be obtained by integrating integrating the current over a codimension 1 or line in 2D, and there's a weighted by alpha. Right? Okay, so and the topological operator for the Z2 charge conjugation is eta, and the fact that we call it the charge conjugation but not the arbitrary Z2 is that it flips the charge of the U1. So this is Q, so eta set maps Q to minus. Or in terms of this commutation relation between the symmetry generators, so you have this. And so far this discussion is abstract, but you can think of one example, keep in your mind, which is the compact boson. Let's call this Q, and Q is the compact boson. In the compact boson, this U1 is the U1 shift symmetry. That's shift phi. Actions like this. And this U1 shifts phi by phi to plus alpha, and this Z2 maps phi to minus phi. So this is one example, but the discussion applies to arbitrary example as long as they have this kind of symmetry. Okay, now where is this interesting continuous non-invertible symmetry or cosine symmetry that I mentioned over there? So to get this interesting symmetry, so what we need to do is to do operation of this theory Q. So let's consider another theory obtained by gauging the charge configuration symmetry of the theory Q. So then let's ask, what are the symmetries in this new theory? In this new theory, so let's see. So is there a U1 symmetry? Well, this because the U1 is not invariant under this Z2 charge conjugation transformation, and because we already gauged the charge conjugation, so only the U alpha equals to pi element survives, commute with the charge conjugation. So this guy survives under gauging. But then you may naively conclude that this symmetry it gets reduced from the U1 in theory Q to Z2, where Z2 is generated by this particular element because it has satisfied the order 2 fusion rule. Okay, but so this is a naive expectation. But now we can be more general and follow this philosophy that we no longer ask for a unitary operator that survives under gauging, but we also allow for non-unitary operator, in particular, the sum of the unitary operator. So in particular, this combination is invariant under 8, right? So let's give it a name. This guy is invariant under the Z2 charge conjugation. So it survives under gauging. Any problem? Okay, so, and also this operator is not invertible. It's not a unitary operator, and it satisfies the famous fusion rule, same as the cosine function. Or maybe to be more explicit, you can just plug in the expression for U, and this will just give you the 2 times cosine of alpha for J. And that's why this symmetry is called the cosine. Okay. But turns out that this expression is not quite right, and that's why I put a quotation mark in here. The reason is that we not only need to require that the operator that survives is invariant under the global Z2 charge conjugation transformation, but also the gauge the charge conjugation transformation, because we already gauge it. But this operator is only invariant on the global transformation, but not the gauge transformation. So there's some problem with it. So what is the more precise way to understand this transformation, this new operator? A more precise way it can be constructed as follows. So let me see, okay. So the more precise way is as follows. So let's start with a U operator in theory Q. And let's ask what this operator becomes after you gauge the Z2 charge conjugation. Well, consider the gauging the Z2 symmetry amounts to consider the interface, the topological interface. Between the Q and the Q mod Z2. And this topological interface can be constructed by gauging on half space with Dirichlet boundary condition for the Z2C gauge field. And yeah, this is the famous half gauging construction, and has been used a lot in constructing a non-invertible symmetry in recent years. But here, this is not a symmetry because this is just an interface between the two series. But this interface is topological. Okay. And now let's ask what this operator becomes after gauge the charge conjugation. So what do we do is to sandwich this interface, this symmetry operator with those two interfaces. So let's just do the sandwich. Maybe I need to use power. So these two are interfaces, and the left hand side is the Q mod C, right hand side is Q mod. And let's erase this part. Okay. And because these two red interfaces are topological, so we can just make them to be very close to each other and effectively regard this whole thing as an effective interface. And that's what we call NR, which is yeah. Now, it's easy to check that this alpha satisfies the same fusion rule as the cosine symmetry, as this cosine function. But maybe I'll just skip that for the sake of time. Okay, so this is the more precise way. This is the more appropriate way to define this new thing. Okay. Good. Same way, yeah. So yes. Maybe let's convince you a little bit more. So for example, one property of this alpha is that the even function of alpha, right? Because cosine functions are even functions. This is also true here. Why is that? Because you can insert a pair of eta here, and fuse one eta to the left. And because this is a gauge interface, the eta can be absorbed. But then fuse this eta move this eta to the right using this relation. It will become minus alpha times theta here, but they further move it to, it's also get absorbed. And this is minus alpha. Yeah. So this is a more appropriate way to define the symmetry that survives under gauging. Fusion rule. Yeah, so the fusion rule, you can also explicitly check that. Yeah, you can just take the two of these and multiply them. It's easy to check that you satisfy that fusion. Yeah. Okay. All right. Now, let's ask the following question. So we know that the ordinary symmetry, so that this U1 symmetry has a conserved current. And then let's ask whether there is a current associated to this non-invertible symmetry. And this is non-invertible because it's satisfied that non-invertible fusion rule. And also it's continuous because it's labeled by a continuous parameter alpha. So this is an example of the continuous non-invertible symmetry. And now let's ask whether this continuous non-invertible symmetry is associated with a conserved current. So how to see it? Well, we can just trace back to the theory before gauging. Before gauging, this symmetry comes from the U1, so it has a conserved current, J. So let's do the same exercise. So you have a conserved current, J. And let's ask what this J becomes after you gauge the Z2 charge conjugation. So you just do the sandwich again. And you just collapse the sandwich. So you'll become, yeah, okay. So before moving, collapsing this sandwich, let's first notice that this J is odd under the Z2 charge conjugation. So under Z2 charge conjugation in theory Q, this J is mapped to minus J, right? So this is charge conjugation. And so it means that this J is an order parameter for the Z2 charge conjugation. So now you can move this line toward the left. And because this is the order parameter, so after you move, then it will become something like this. Here. And this is a disorder operator. So this is the order operator, or order parameter. The two charge conjugation. And this is a disorder. For the dual symmetry after you gauge the charge conjugation. So this is quite like the Ising model, where this line is like a duality line, and when it moves across the order parameter, you will get a disorder parameter. And the same thing happens in here. And then you can move these two lines together, and it will become the 1 plus eta hat, where this hat is the quantum symmetry. I mean, use white color. So this eta hat, and this will become 1 plus eta hat, but attached to a j. And then you can like, this is topological, this is topological, this is topological. Everything topological besides this point, where j depends on the position x. And you can you can move this line on top of this j. So j will be on top of this line, and yeah. So this is the configuration you get. So that's the non-local current that I really mean over here. The non-local means that in this picture, non-local means that these are conserved current, but attached to a topological line. And over here, non-local means that it's a conserved current living on the topological line. But these two configurations are equivalent to each other. Actually, the left one implies the right one. Yeah. Also, the right one also implies the left one, as I'll explain later. Yeah. So this current in the CFT is 1, 0 operator, and this is the scaling dimension, right? So this is the conformal weight. Conformal weight does not get changed after you gauge. So this is also a 1, 0. And you know that the 1, 0 is is the same as the conserved concept. Okay. So there are two. Yes, then you will be more. It's more complicated. Yes, I'll briefly comment on this. That's right. That's a good question. So, indeed, more generally, so this construction can be generalized to arbitrary G mod H, where G is a continuous set and H is a discrete but non-normal subgroup of G. And this is called a coset symmetry in general. This is called the coset symmetry, which I learned from this paper. And in this paper, they give a more precise definition, more precise name. They call it a double coset symmetry. But anyway, so what do what they mean is the same. Like you have a G symmetry, you just gauge H, and you use this sandwich construction. And in our example, H is the Z2 charge conjugation, and the G is the U1 semi-cross Z2. Yeah. Okay. Okay, so these are quite general construction and it can be applied to arbitrary dimensions. Now, you can ask like whether this construction is useful. Well, it can give us many examples. So that's also that's one use of this construction. But if you want to understand, for example, what does whether we can use it to understand, say, the new consequences of G flows, then this construction is not quite useful. The reason is that whatever consequence that you can get from this non-invertible symmetry, you can always trace it back to the G symmetry before gauging H. And because the gauging operation is a topological operation which commute with the renormalization group, so essentially that means that you don't learn anything new from studying this non-invertible symmetry. So whatever you learn from this G symmetry, you can always transfer that to the non-invertible symmetry by doing gauging. Okay, then the question is, can we find more examples? More examples that beyond this coset construction. Yeah, and second, we also observed that so on one hand, the symmetry operator we get is a non-invertible operator, and also on the other hand, this current we get is a non-local current. But is there really a relation between them? Like one implies the other, or something like that. So is there is it just a coincidence that the non-invertibility is contributed to this non-localness of the conserved current? So, and this is precisely the generalized Noether theorem is telling us. Symmetry and non-local conserved current. They appear together not just by coincidence. They appear together for a reason, and the reason is that there is a generalized Noether theorem. And that's the third part of the talk, which is to explain the generalized Noether theorem. Okay, so before moving on, are there any further questions? Yeah. What's the operator that carries charge? Yeah, so that's a good question. So I think whatever that is charged on the original U1 is also charged on the non-invertible symmetry. Sorry. What happens with that object? So you have, before gauging, you have e to the I phi. And after gauging, this guy becomes this guy. Yeah, maybe this guy becomes like you do the sandwich. And it becomes non-local. Yeah, it becomes non-local. And then this non-local operator can, like this topological operator, can act non-trivially on this non-local operator. I haven't worked out, so yeah, it should be some operator in the twisted sector. Yeah, that's a good question. Mm. Yeah, yeah. Oh, and just like this is a well-known fact, right? So like an order operator, if you do the gauging, becomes a disorder operator. Or maybe I can be more pathological. Why is eta hat? So before gauging, this J is charged under the Z2, right? So this J is charged on the Z2. So if you turn on the background field for the Z2 symmetry before gauging, like if you turn on the background field for the Z2 charge conjugation, then this J should be attached to the background Wilson line, right? So let's call it a C. And then after gauging, this C is promoted to dynamical field, and the e to the IC is precisely eta. Yeah. All right. So generalized Noether theorem. Okay. So let's first consider this direction. And this direction, actually, as I have already told you, has already been discussed in nice paper by Ryan Songeren and Ethan Wang. Maybe let me just quote the result over there. Songeren. One. So what do they say in the paper? They find is that whenever you have a topological line operator which is labeled by continuous parameter alpha, then there's always a 1, 0 or 0, 1, which doesn't matter. So 1, 0 operator, for instance, living on this line. The reason is that this operator, because it's topological, so there must be an exactly marginal operator. And exact marginality means that the scaling dimension must be 1. And also it's topological means that its spin must be 1. And the scaling dimension, the spin constrains the quantum conformal weights to be 1, 0 or 0, 1. So this part doesn't use the fact that this line is non-invertible. And it also works for when the line is invertible. But where does non-invertibility comes in? Well, if you can further fold this alpha and alpha here. And along this operator, let's call it a J. And then because this operator is topological, so you can fuse in the middle part, for instance, and you will get something like you will get this diagram. You just fold in the middle, and in general, if so you will get many fusion channels in the middle, which I call L. And then you can try to squeeze this bubble, and after squeezing that, you will get just an effective current living at the end of the line L. Now, if N alpha is invertible, so when N alpha is invertible, then this channel must be identity. Right. So then it means that this J is no longer attached to L. So you get a conserved local current, which 1, 0 operator, which is local. And this is precisely the conventional Noether theorem is telling us about. But when an alpha is non-invertible, then you can get more than identity channel. And then you will generically get a J living at 1, 0 operator living at the end of some non-trivial line. And this line, in many cases, are discrete, so they don't carry this continuous parameter alpha. But there are also cases when this L is continuous, like labeled by a continuous parameter. But the upshot is that when an alpha is non-invertible, then you will get the J living at the end of some non-trivial topological line L. Yeah. So that's this direction. So you'll get a non-local operator. How about the other direction? For the other direction, let's recall the invertible case. That how do we use the conserved current to construct the topological operator? So whenever we have an action, then so the puzzle is as follows. The puzzle is that you usually will say that you have an action, you have a J, and then you can construct this charge, and then you typically exponentiate it, and you claim that it is a topological operator. And this operator being topological means that it comes from the fact that this Q is also topological. But there is a question of, like, why do we just take this particular function of Q? Why not any function of Q? This is also a topological operator, but why don't we consider that? Okay, so the reason is that only this operator gives you a well-defined sense of Hilbert space, a definite Hilbert space. Why is that? So how do we understand this? We start with the action, and then to insert a defect topological operator into the partition function, what we usually do is that we modify the action, or we deform the action by turning on this current J, or sometimes we write it as like turning on this guy, where A dictates the location of this this line. And then this means that in the positive, so this gamma can be in arbitrary direction. If it lies along the space direction, then it defines the operator. But if gamma lies along the time direction, it becomes a defect. And then it means that in the path integral, this guy, let's say the Euclidean signature. So you'll become J. And this guy, or maybe this guy. And this guy is precisely the topological operator that we insert in the path integral. So this is the construction of the topological operator from the conserved current. So in one sentence, you started with in the path integral, you started with a trivial line, and you deform the action by integrating this J over this trivial line, and then you're done. You get this operator. Now, for the non-invertible symmetry, so what do? We do similar thing. for non-invertible symmetry, instead of starting with the trivial line in the path integral, instead of starting with a trivial line, let's just insert a non-trivial topological line, B. Okay. And then, so let me say more precise. So for the non-invertible symmetry, so we start with a current living at the end of some line. So let's call it L. And then, so this is a non-local current. So we have to worry about what happens on the other end of the line. So the idea is that let's find another topological line. Let's call it B, which has a non-trivial junction, topological junction with the topological line L. And this topological junction, let's call it X. And then if you move this J on top of this baseline, so let's call it, this is the baseline. Then this is just some currents living on the baseline. Now, then to construct a topological operator, what you really do is that you first insert this baseline in the path integral, and you just deform the action by this current, but supported on this baseline. Okay, and this defines you the insertion of this non-invertible operator, topological operator, supported on this baseline gamma. Yes, it depends on the baseline. So current, you can have many baselines sometimes, and they will give you different topological operators. Yes. Which is non-local? Yeah. So this J is living on the line, and the line is topological. So yeah, so it's a non-local indeed. This is a non-local current in the sense that I introduced earlier. Yep.
So the phase deformation does not break all of the
Well, you have to tell me like what are the symmetries of the original system. So here I'm claiming, yeah, yes, I'm claiming that this line, this operator is the symmetry of this original system. Yeah. 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 Sometimes you can. Right. You can, so I'll give you a bunch of examples where like one can find many lines, but I will not say that they are classified because like there can be more lines. Yes, yeah. So in all the examples, we already know these like baselines and Ls. You'll see the example in the example. in this. No. So this L is hidden in the. So maybe let's call it effective. So the information of X, L, and J is packaged into this definition of L effective, J effective. So the information of L is still over there. Yeah. Effective, they are the, you mean for different L's will get the same symmetry? No. Yeah. Okay. Yeah, so this is the definition of this non-invertible symmetry. So I'm claiming that this is a topological line, but I really need to prove that. And so you may say that why this is a topological? Actually, this is a very non-trivial task. We spent maybe over a year to come up with a proof for that why this line is topological. The main subtlety here is that this baseline as well as this L can act non-trivially on J. So like if you have another, if you have another, say you have two J's, then if you go one goes through the other, then this L can act on this J. So there are various subtleties like that. And it bothers quite a lot, but eventually it worked out, and the thing you only need to prove that in CFT, so we are only able to prove that this operator is topological in conformal field theory in 1+1 dimensions. And in that case, what you need to prove is that this guy is 0 and this guy bar alpha is 0. And in a CFT, there's a standard technique to compute this correlator, like in Pochinski and in many string theory textbook, CFT theory textbook. And then what you do is that you start from this expression, you do the Taylor expansion in terms of alpha, and you prove that this commutator vanishes order by order. So yeah, so in CFT it works, but in general, there's no conformal symmetry, no Ferrari symmetry. So this computation doesn't directly generalize to non-conformal case, and we still don't know how to prove that it's topological. But at least in CFT they are topological. Okay. Right. Okay. So see how much time? I think the time is already up. So maybe let me spend 10 minutes. Is that okay? Maybe 10 minutes to quickly go over some examples. So yeah, actually I want to say I prepared 3 type of examples. One is in one of the fun examples. Okay, so the idea to find these symmetries is to first find the non-local current. So to find the non-local currents, and then use this construction to give us the topological operator or non-invertible symmetries. And then the question boils down to like in which CFT there is a 1, 0 operator attached to some topological line. And in the simplest example that you may hope to start your search is the minimum model. In the minimum model, we know the Pachin function, we know the operator spectrum. So it's possible to scan through the spectrum and try to see that whether there is this non-local current. And turns out that there's no conserved current in the twisted sector. Like there's no ordinary symmetry, which is ordinary continuous symmetry, which is well-known fact in the minimum model. And it turns out that there's also no non-invertible continuous symmetry in the minimum model. Okay. And the first non-trivial example is the C equals to 1 theorem, because minimum model are below C equals to 1, C smaller than 1, and the first non-trivial example is C equals to 1 CFT. The modular space of the C equal to 1 CFT is as follows. So it's R, R circle, the circle branch, this is orbifold. And this is R equals to 1, which is the same as the to level 1, square root 2, 2, etc. And there are also 6 points. Well, this is just the in the circle branch, it's just some compact boson, which I wrote down the Lagrangian previously, and you can work out the local operators. So this is something like e to the I alpha phi, e to the I. Let's see. Yeah, so this is e to the I beta 6 theta. So what is this theta? Phi is just a compact boson. Phi. And it's well known that this is a T duality. T due to theta. So on the T due, phi and the theta shift are exchanged, and R is maps to the 1 over R. And it's known that the primary operators are phi I W theta. This is local primary, and you can also work out the scaling dimensions. And well, if you relax that these coefficients are integers, then there will become lines attached to, they'll become operators that are attached to topological lines. So it's attached to, it's a become non-local operator attached to L beta M L alpha winding, where this is the topological operator generates the momentum symmetry. And this is the topological operator generating the winding symmetry. So L alpha, say, winding is alpha over 2 pi E phi, and similar for that. Okay. You can work out the scaling dimension of this, and you demand that this is a 1, 0, and solve for the scaling dimension. The scaling dimension is something like 1 over 4 alpha over 2 R plus beta R over 2 pi squared, and this is 1 over 4 alpha over 2 pi R minus beta R over 2 pi squared. Demand needs to be 0, demand needs to be 1. You solve for alpha and the beta, you will get the following result, that there are 2 conserved currents, R. So this is alpha equals to plus 2 pi R, beta equals to 2 pi over R. And you can also get a R minus, where the plus sign becomes the minus sign. So the upshot is that for each R, for every R, there exists 2 primary operators, non-local, primary operators with scaling dimension 1, conformal dimension 1, 0, and another two 0, 1. And together with the current, like the momentum and the winding current, they become 3 non-local currents. So, well, there are 2 non-local and 1 local. And also, so these are the 3, 1, 0, and there's another 3, 0, 1. And so it means that for every R on the circle branch, there is a non-invertible. There are 2 non-invertible symmetries coming from these 2. Well, there are 4 non-invertible symmetries. 2 come from the 1, 0 operator, and 2 come from 0, 1. And if you work out the details, you will find that when R equals to 1, these non-invertible, these non-local currents become local currents. And these local currents will precisely generate the SU2 symmetry. So in the R equals to 1 theory, there is a SU2 times SU2 symmetry. These are, each SU2 is generated by 3 local currents. And it turns out that if you crank up the R, 2 of the conserved current become non-local and becomes non-invertible symmetries. Yeah, so this is the global picture of this example. And it turns out that if you restrict to the case when R is rational, then the R equals to 1 and R equals to, say, P over Q are related by gauging. And this is precisely the gauging that makes this operator non-local, which is very similar to the idea that we encountered in the second part of the talk. Is the cosine construction, coset construction. Yeah. Okay, so this is the first example. The second example is the Wezumino-Witten model. For simplicity, let's just focus on SU2 level K. You can also search for the non-local currents living at the end of some topological line. And here we know that there are K plus 1 Felindy lines. And you know that how these Felindy lines act on the local operators. And you also know the S matrix for these Felindy lines. So, so you can work out the defect spectrum for these Felindy lines by doing this modular transformation. So the idea is that you start with the partition function with nothing inserted. You then insert a Felindy line in the space direction. You do a modular transformation. You get this. And by doing the Q expansion of this partition function, you'll get the spectrum of this non-local current that attached to this Felindy line L. And it turns out, and you ask whether there are, in this spectrum, there are 1, 0 operator in this expansion of the partition function. And it turns out that there are. So turns out that when K equals to n plus 2 times n minus 1 case, when for n is an integer and bigger or equal than 2, there are examples of the Felindy. Yeah, there exists a non-local current attached to L2n, where this line, so the Felindy line is labeled by lambda, and lambda runs from 0, 1 up to 8. And there are many examples. Oh, by the way, so for this equal to 1 example, you'll see that all of them come from, at least when R is rational, all of them come from the coset construction. So they are not that interesting from the perspective of the renormalization, as I mentioned earlier. Yeah. And for this example, so in the first case, for n equals to 2, so k equals to 4, and there is a current living at the end of L4. And it turns out that this L4 is a Z2 line. And you can ask like whether you can do some gauging to remove this Z2 line. And it turns out that there is. You can gauge L4, and you will get SU3 level 1 theory. So this non-invertible symmetry is not intrinsic, and it comes from another theory by doing some gauging. The next example is 3, which called parameter k equals to 10. And in this case, there's also a non-invertible symmetry in non-local currents attached to some topological line, but in this case, it's non-invertible. So this case, this finity line is non-invertible, but nevertheless, you can always gauge it. Why do we know that you can gauge it? Because like in this case, there's an ADE classification for ADE classification, which classify the modular invariant partition function of the SU2 level K. And different modular invariant partition functions are related by gauging. So from that data, you know that this line, whether this line can be gauged away or not. Well, but that gauging has assumption that the gauging preserves the SU2 chiral algebra. So here, when we say that whether they can be gauged away, we really mean that we gauge whether this line can be gauged away while preserving the SU2 chiral algebra. So in general, you can do more general gauging, but nevertheless, in this case, you can also gauge away. So you can gauge L6, and you will get some other theory being 5 level 1. So it's also not intrinsic in some sense. And the next example, in this example, it's interesting because this is also non-invertible. But in this case, the ADE classification tells us that you cannot gauge, this line cannot be gauged away while preserving the SU2 chiral algebra. So it's a first example that at least, it's the first example that we don't know whether, it's the first example that is beyond this coset construction, at least when if you assume that the chiral algebra is preserved. Yeah. So there can be more general gauging that does not preserve SU2 chiral algebra. Yeah. So let's call it the conditionally intrinsic non-invertible thing. And you can go up, crank up in this list. And in this case, you can also be gauged away. You will get G2 level 1. But it turns out that when K is bigger or equal than 6, all of them are conditionally intrinsic. Okay, so this is, so that's why this example is interesting, because it provides us like new examples that possibly beyond the coset construction. And the last example I want to mention, maybe, yeah, maybe 4 minutes. So 3 minutes. So the last example is well, in the beginning we said that in a single copy of minimal model, you don't have this non-invertible continuous symmetry. But how about take the two copy, like let's take the minimal model in the unitary series, that M and M bar. So how about in this model? So in this model, it turns out that there's no continuous ordinary global symmetry. So no, I mean, invertible. But there is a continuous non-invertible. Yeah, orientation reversal, or like if you, yeah, it's precisely the orientation reversal. You just do this parity transformation. Yeah. So you flip the spin, for example. You just make the left mover and the right, exchange the left mover and the right mover. These are bosonic. Oh, what I mean is that like edge left, edge right, map to edge right. Edge. Oh, yeah. Okay. So yeah, so by this, what I mean is that there exists, we found many examples where you have this 1, 0 operator living at the end attached to some Bernini line. Yeah, I don't, I'm not sure. I think even if you, without the bar, you still can find some non-invertible symmetry. But the reason I insist that there is a bar is as follows. So it's just for the purpose of application. But the reason is as follows. So here, I claim that in this case, you have a bunch of, for some m, like a sequence of m, when m equals to 3, 8, 10, 11, there is like this infinite series sequence. And in this sequence, there exists such an operator. And when m equals to 3, this is the icing. But there are many others. And the reason that I want to take a bar over here is as follows. So if you take this like m times m bar, and then it allows you to do the unfold. So it's m times m bar. Then if you do the unfold, then you will get this guy. So this is n and n. Okay. And in this theory, there is a non-invertible symmetry, as I see. And if you put it on a boundary, and typically this boundary would not preserve this non-invertible symmetry because this symmetry is a chiral. It's a 1, 0 operator. So the boundary condition typically don't preserve that. And then it means that if you start with one particular boundary condition, you fuse a non-invertible symmetry line onto the boundary, you will get a family, continuous family of boundary conditions. And after unfolding, you will get a family of like conformal defects in a single copy of minimal models. Yeah, so and this is called the defect conformal manifold. And in the case when alpha m equal to 3, this has been already very thoroughly explored by Masaki Yoshikawa and Alan Affleck. Yeah. And surprisingly, there are many, like very few works exploring other conformal manifolds that go beyond the Ising model. The reason at that time they can do it is because if you fold the Ising model, this is just the C equals to 1 theory. And people study the C equals to 1 theory a lot. And they can explore the boundary conditions and then do unfolding, you can get this conformal effect. But if you go to higher m, then the central charge of this guy is greater than 1, and it's much less control. The boundary condition is much less under control. And then correspondingly, as a consequence, the defect conformal manifold is less well understood. But now we see that there are guarantees to be found like many defect conformal manifold just because the existence of non-invertible, continuous non-invertible symmetry. Yeah, from this model. Yeah. Okay, so maybe let me stop here. Yeah, thank you very much.
Thank you for the wonderful talk. Are there any questions?
Yeah.
Say something about mismaking this
KT phase transition. That's a good question. I don't know. Continuing invertible symmetry. Yeah. It becomes basically some. Yeah, it becomes some. Yeah, because that KT transition corresponds to K R equal to 2, right? So yeah, R equals to 2. So in that case, there is an R equals to 1, R equals to 2, they differ by factor of 2. So in that case, they are related by gauging. Yeah, so I don't think maybe, yeah, precisely because they are related by gauging, I'm not sure whether you will get something new out of from this non-invertible symmetry. Yeah. Do we know the Felingi line? Or do we know some topological lines in the? This is a non-compact theory, right? Yeah. That's outside of my comfort zone. So
if there are no more questions, let's send Professor Yunqin again.